First, I start with my materials: a protractor, straw, and like a string that's 6 to 10 inches and a small weight to hold it down. And I start taping the straw to the protractor on the flat side and making sure that it's secure. I grab our 6 to 10 inches string and tape it to the top only. Then I move on to the weight that's kind of like allowing the string to move back and forth when you're measuring the angle. And after this, it's ready. And now I'm showing you how to use it, and we are going to measure the distance from the flag to me, and it's like around like 75.
As you guys can see right here, Mika is standing with the clinometer 100 feet away from the rocket. From here, we can measure how high the rocket flies, making a perfect right triangle. From here, we can set up a formula, which is height is equals to the distance times tangent of the angle.
Once the rocket starts to take any path that is not straight, in this case a curve, it becomes difficult to calculate the maximum height of the rocket. You would now need 2 people with clinometers to measure the rocket. This is due to the fact that the rocket is now no longer flying directly over the launch pad, making the distance unknown to the person measuring, since the distance of the rocket changes from its initial straight path. Having 2 people measure 2 different angles of the rocket allows them to accurately measure the rocket's position compared to having one angle that can correlate to multiple heights. I'm going to quickly explain how we use the law of sines to find the equation for the height of the rocket. So to start, the law of sines states that for any triangle, the ratio of the side lengths to the sine of its opposite angle is constant for all 3 side angle pairs, which just means they will be equal to each other. So we wrote those ratios down first. And to explain the first ratio, 200, we got it from the base of the distance between person A and person B, as they're both equally 100 feet away from the launch pad, but put together is 200. And then we have that over sine of 180 minus alpha plus beta. This is simply because those are the 2 known angles, and we subtracted it from 180 because all triangles, their angle is equal to 180. And then we simplified it to sine of theta, and then we substituted that for its original complex form. So that ratio will be simplified to 200 over sine of alpha plus beta. And then to find the distance between person A and the rocket when measured, we decided to make a smaller triangle, as you can see represented from the dotted line, and that dotted line will represent the height of the rocket and the third side of this smaller triangle. So we will set up the equation that we just found: 200 over sine of alpha plus beta equal to AR over sine of beta. And to get AR by itself, since that is the distance we're looking for, multiply sine of beta to both sides, and that gives us AR is equal to 200 sine of beta over sine of alpha plus beta. And then we can use this newfound equation to find the height. So we will do sine of alpha is equal to height of the distance between person A and the rocket, which is just AR. And this is using the sine ratio of opposite over hypotenuse. And we're looking for h, so we're going to get that variable by itself by multiplying AR to both sides, which gives us h is equal to AR sine of alpha. And since we found AR earlier, we can plug what we found into the place of AR as a substitute. And this gives us h is equal to 200 sine of alpha times sine of beta over sine of alpha plus beta.